Hello. This will be a demonstration of proposition 3 from book 8 of Euclid's Elements, which says that if any number of numbers be in continuous proportion and be the least in that ratio, then the extremes of that continuous proportion will be prime to one another. This is just the converse of proposition 8.1. So remember on that one, we were given that the extremes were prime to each other, and we wanted to prove that that continuous proportion was the least in that ratio. Instead, we are given the converse, which is that the geometric sequence, the continuous proportion, is in least ratio, and what we want to prove from that is that its extremes are prime to one another. All we're given is some geometric sequence, some continuous proportion of A, B, C, and D. We're also given that this continuous proportion of A, B, C, and D is in simplest terms. Those are the least numbers which have the same ratio with them. And what we want to prove from this is that the extremes of that sequence are prime to one another. In this case, that is that A and D, those two numbers, are prime to one another. We're going to begin by employing proposition 7.33 by taking two numbers, E and F, such that the ratio that E has to F is the least, or E and F are the least numbers which have the same ratio as A, B, C, and D have to each other. So remember, A, B, C, and D are continuous proportion. So A is to B, just as B is to C, just as C is to D. What we're doing is we're just taking one of those ratios, namely A to B, for example, and we're putting it in simplest terms. A particular numerical example of this would be if you had the geometric sequence of 8, 12, 18, and 27. What this step would be doing is you would take the 8 and the 12 and you would reduce it to simplest terms, which would just be 2 and 3. So that's all we're doing here. Next, we're going to use proposition 8.2 twice in a similar manner to proposition 7.33. What do I mean by that? What I mean is that we're going to take three numbers, G, H, and K, such that the continuous proportion of G, H, and K has the same ratio as E and F and is likewise in least terms. It being in the same ratio as E and F means it's also in the same ratio as A, B, C, and D. Again, a particular numerical example helps to illustrate this. So again, say we had the sequence 8, 12, 18, 27. What we would be doing here is finding a three-term continuous proportion, a three-term geometric sequence that has the same ratio of 8 to 12, 12 to 18, or 18 to 27. What that would look like for this example of 8, 12, 18, and 27, we would find the sequence of 4, 6, and 9. So 4 has to 6, the same ratio that 6 has to 9, and both of those are the same with 8 to 12, 12 to 18, and 18 to 27, namely that each are just 2 to 3 ratios. So again, that's all we're doing here. Now, the final step of this is we're going to take a geometric sequence, a continuous proportion that has the same number of terms as our given continuous proportion that is also in the same ratio as E and F and is least with E and F. We're going to call these L, M, N, and O, because remember, we were given a four-term continuous proportion, so we're just taking four numbers, L, M, N, and O, and these four numbers will be in continuous proportion and will be least of those which have the same ratio as E and F, which also means that they're the least of those which have the same ratio as A, B, C, and D. Now, you might already be wondering, okay, well, if A, B, C, and D, those numbers are the least which have the same ratio with them, L, M, N, and O are the least numbers which have the same ratio as the least, wouldn't that just make L, M, N, and O equal to A, B, C, and D respectively? And you're exactly right, but we're going to get to that later. First, we're going to establish that because E and F are in simplest terms, their ratios in simplest terms, they are the least of those which have the same ratio with them. We made them that way in the first step. We can say by proposition 7.22 that our two numbers E and F are therefore prime to each other. And being prime to each other, it of course follows that their cubes are also prime to each other. We know this by proposition 7.27. So we know that not only is E prime to F, E cubed is prime to F cubed. Now, we know that E cubed is the number L and that f cubed is the number O. How do we know this? Well, we know this because we made the numbers L, M, N, and O to be least in the same ratio with E and F. And we can use the porism of the previous proposition 8.2 to tell us that because L, M, N, and O are in simplest terms, they are in least ratio, their extremes have to be cubed because it's a 4-term continuous proportion. So L and O are cubes. And we know, because of how we construct such continuous proportions, we know that the extremes are simply going to be our original two numbers cubed. So we made L, M, N, and O to have the same ratio with E and F. So we know that their extremes are just going to be E cubed and F cubed. That is, that L is E cubed and O is F cubed. So because E cubed is prime to F cubed, we established that in the previous step, and E cubed makes L, and F cubed makes O, we can of course say, just by a property of numbers, that the two numbers L and O are prime to each other. L is prime to O. Now, again, you remember that thing you might have noticed. If A, B, C, and D, or not if, since they're the least of those in that same ratio, and the same is true of L, M, N, and O, it therefore stands to reason that our four numbers A, B, C, and D are equal to our four created numbers L, M, N, and O respectively. Namely, that A is equal to L and D is equal to O. So of course it follows that because L is prime to O, whatever they are equal to will also be prime to each other. It's just a property of numbers. So because L is prime to O, L is equal to A, and O is equal to D, we can therefore conclude that A and D are prime to each other, which is exactly what we set out to prove, which means we are done with the proposition, therefore, etc., Q, E, D. This, I'll admit, is just a bizarre proposition. I hope I explained it well enough. I felt like I was kind of wandering and meandering at certain points, but I hope it made enough sense. Of course, before I end the video, I just want to give a particular example of this. So again, let's not use 8, 12, 18, and 27. I use that one a lot. Let's use 27. This next one would be 36. Next one would be 48. And the last one would, of course, just be 64. Now, this is a 4-term continuous proportion, and we know that it's the least with this particular ratio, namely a 3 to 4 ratio. You'll notice that each of the terms taken 2 and 2 together have the same ratio as 3 and 4. So 27 is to 36, just as 3 is to 4, 36 to 48, just as 3 is to 4, and 48 to 64, just as 3 is to 4. So you know that this 4-term continuous proportion is the least with that ratio. And what we can conclude using this proposition 8.3 is that our extremes are prime to each other. Our extremes here are 27 and 64, and so what we can conclude from this is that 27 is prime to 64. This is obviously true, so we see that this proposition holds, which is always reassuring. That's all I've got to say about this one, so I'll end the video here and move on to proposition 8.4.